What if the world around you, the very fabric of reality, isn't actually solid until you look at it? What if the universe itself was just a blur of possibilities waiting for you to make it real? That's not some far out sci fi plot. It's a mind bending idea rooted in the strangest corner of science: quantum mechanics. For decades, some of the smartest minds on the planet have grappled with a concept so bizarre it turns our everyday understanding of existence on its head. We're talking about the idea that particles, and perhaps even the vast cosmos, might not have definite properties until they're observed. It's a core tenet of something called the Copenhagen interpretation, championed by giants like Niels Bohr and Werner Heisenberg. They basically said a physical system doesn't make up its mind about what it is until someone or something measures it. And if that sounds like pure magic, buckle up, because we're about to dive into why scientists even dared to suggest such a thing and what it could mean for everything we think we know. To even begin to grasp this wild notion, we need to understand a few fundamental ideas from the quantum world. First up, there's the wave function. Imagine this as a mathematical recipe, a sort of instruction manual for a tiny particle. Before you observe it, this wave function doesn't tell you exactly where the particle is or what it's doing. Instead, it describes all the potential places it could be, or all the potential states it could be in. It's like having a blueprint that shows every possible house you could build on a lot, but no actual house has been built yet. This leads us to our second big concept: superposition. This is where things get really weird. Before observation, a particle isn't just in one place, it's in all possible places or all possible states simultaneously. Think of it like a coin spinning in the air. Is it heads or tails? It's neither, and it's both, until it lands. Until it's observed, that coin is in a superposition of both heads and tails. It's not a definite head or a definite tail, it's a blur of potential realities all happening at once. The most famous, and perhaps most unsettling illustration of this idea is Schrödinger's cat. You've probably heard of it. Imagine a cat locked in a steel box with a tiny vial of poison. The poison is linked to a radioactive atom. If the atom decays, it breaks the vial, and the cat dies. If it doesn't decay, the cat lives. The catch? The atom, due to quantum rules, is in a superposition of both decayed and undecayed states until it's observed. So, according to Schrödinger, until you open that box and look inside, the cat is neither alive nor dead. It's in a fuzzy, bizarre superposition of both alive and dead. The act of opening the box and observing the cat forces it to choose one reality: alive or dead. Before that, it was just a quantum mess. Now, if you think this sounds like thought experiments cooked up by mad scientists, think again. The foundation of these ideas comes from very real, very famous experiments. The most iconic is the double-slit experiment. It's been called the most beautiful experiment in physics, and it's the clearest example of what we call the observer effect. Here's how it works. Imagine you have a wall with two tiny slits in it, and behind that, a screen. If you fire tiny particles, like electrons, at this wall, what do you expect to see on the screen? If electrons are like tiny balls, you'd expect to see two distinct lines of impacts on the screen, right behind each slit, just like firing bullets through two holes. Simple. But that's not what happens when these electrons are left unobserved. When nobody is watching, the electrons behave like waves. Instead of two lines, they create an interference pattern on the screen, multiple bands of hits and misses, just like water waves passing through two gaps and creating ripples that overlap. It's as if each electron passes through both slits at once and interferes with itself. It's utterly baffling. However, the moment you put a detector near the slits to observe which slit each electron goes through, everything changes. The electrons suddenly stop acting like waves and start behaving like ordinary particles again. They only go through one slit, and they make those two distinct bands on the screen, just like bullets. The act of observing forces the electron to choose a path, and in doing so, its wave function collapses and it snaps into a definite particle state. It's not just a subtle change, it's a complete transformation in behavior. This isn't just about measurement, it's about the very nature of reality shifting based on whether it's being looked at. This brings us to arguably the most crucial and troubling question in quantum mechanics. What exactly constitutes an observation? Does it require a conscious human mind, someone actively thinking, I am observing this? Or is it simply any interaction with the measuring device, even if that device isn't conscious? The original Copenhagen interpretation generally leans toward the latter. It suggests that consciousness isn't explicitly required. An observation is essentially any interaction that forces a quantum system to collapse from its state of superposition into a definite reality. If an electron hits a photon, a particle of light emitted by a detector, that interaction counts as an observation, even if no human is looking at the detector screen. This means the detector itself, even a simple atom, can be an observer in a quantum sense. Consider our distant star example. An atom in that star might be in a superposition of decayed and undecayed states. It doesn't decide whether it has decayed until it interacts with something else, perhaps emitting a photon that then hits another atom, or its decay products bump into other particles. That interaction, that measurement, is what forces it to choose, even if that choice happens billions of light years away from any human eye. So, while the phrase, the universe may not exist until you observe it, is catchy, the quantum you might not need to be conscious in the way we usually think. But if observation, even non-conscious observation, is what solidifies reality, this leads to some truly profound implications, especially when we think about the entire universe. This is where philosophers and cosmologists get into deep waters. The biggest paradox: who was the first observer? If everything needed an observer to become concrete, who observed the Big Bang? Who solidified the initial conditions of the universe before any stars, planets, or even simple organisms existed to do the observing? This question led to ideas like the participatory anthropic principle, PAP, proposed by the brilliant physicist John Wheeler. Wheeler, who coined terms like black hole and wormhole, took the observer effect to its most radical conclusion. He suggested that observers aren't just a byproduct of the universe, they are essential for the universe to exist in the first place. Without observers, there's no definite reality. The universe, in a sense, needs to be brought into being by the act of observation. Wheeler famously described the universe as a self-excited circuit. It's not a pre-existing stage upon which life simply plays out. Instead, the universe and observers are intrinsically linked, each bringing the other into concrete existence. Our very existence as conscious beings capable of asking questions and performing measurements might be what solidifies the universe out of a quantum haze of possibilities. It suggests a breathtaking feedback loop where we observe the universe, and in doing so, we help to create it. So, the popular phrase, the universe may not exist until you observe it, while a dramatic simplification, highlights one of the most central and enduring mysteries of quantum mechanics. It's not just a quaint philosophical debate, it's a window into the nature of reality itself. It tells us that reality may not be a fixed objective thing ticking along independently of everything else, like a giant, perfectly pre-programmed clock. Instead, reality might be an interactive process, a dynamic dance that relies on participants, even inanimate ones, to give it form. It challenges our deepest assumptions. We as humans are not just passive spectators gazing upon a ready made universe. Instead, this quantum perspective suggests that we, through the very act of observation, might be active co creators of the universe, playing a far more intimate role in its unfolding than we ever dared to imagine. It's a humbling, awe inspiring, and frankly, mind bending thought. If you found this dive into quantum reality as fascinating as we did, make sure to check out our next video exploring parallel universes.